to construct a uniform distribution, we need to find the upper bound, we need to find the lower bound. So if I have to do it in Excel, I just open any Excel sheet. I think that would be better because it is already being opened. So I would open any Excel sheet. I need to define minimum value. I need to define the maximum value, and say minimum value is 0 and maximum value is 1 for the sake of argument. And I need to generate so how many intervals, because it's a we are right now we're talking about a discrete, even discrete distribution. Uniform distribution can be discrete, can be continuous. So let's say I need to sample 1000 values from a uniform distribution. So it means that random variable can take 1001 values. So from 0, 1, 2, sorry, no, to start with the, yes, it's from 0 till, okay, um, let it be for the sake of argument be 10, start with 10. So 0, and then it would be zero point 0.1, so I need to divide it into 10 interval, and then zero point 0.2, and then so on and so forth. I would keep on increasing until unless I would reach 1. So when n is equals to 100, I would divide random variables like that. And what would be the probability associated to that? So probability of getting any random variable would be b minus a upon n. So what is the probability of getting 0? B minus a. It would be b. What is b? B is over here. Minus a is over here. Divided by n. N is over here in this case. So I would try fixing all of these so that it won't get changed when I drag it. So that's why I put a dollar sign over here, and I would put a dollar sign over here, and I would put a dollar sign over here. So that's actually b minus a upon n. So probability of each occurrence would be zero point 0.1 in this case. When random variable is, say, when n is equals to 1000, then how many random variables could be defined behind that, between that? That would be 0.01, and then 0.02, and I have to move on until and unless I reach 1. So what is the probability of each uh, occurrence? So that would be b minus a upon n. So except for the n is from b3, I would write b4 because I'm talking about. So the probability of occurrence of each event would be 0.01. So this is how we can define a uniform distribution. So a uniform distribution could be defined like that. So if maximum is 10 and minimum is 10 and maximum is 100, in that way the probability distribution would be something like that. Of course, n cannot be 10 from in this example. So this won't work for that case because n cannot be 10 in that particular example. So that's why the probability is 9, which is not possible. But over here in this case, there is a 90% chance of getting anything between. So if I need to look at between 10, and then I would have to draw between 10 and then 10.1 and then 10.2. No, it is between 10 and 100. So I need to 10, 20, 30 till 100. I should start with 0. Oh no, it's 10. So I would, and then the formula would be um, maximum minus minima divided by 10. So that would be, no, it cannot be 9. It won't work in under this condition. I think I violated the formula. Anyways, so if you look at this example, there is the probability is defined like that. So it's b minus a upon n. This is the formula with the Microsoft sheet. So it's 1 upon, sorry, it's 1 upon, oh, I was writing it wrong. So it is 1 upon b minus a, sorry. So this is 1 divided by b minus a. That's why I'm getting strange results. So in this case, the probability of each occurrence is like that. It is 1 minus b minus 1 upon b minus a. So the probability of occurrence for each value would be, it won't be zero point 0.9, it would be a reciprocal of zero point 0.9. So reciprocal of zero point 0.9 divided by 10. So 1 upon 9 is 0.111. And if you divide it by 10, so that would be 0.0111. So because n is 10 over this case and n is 100 over this case, but the interval is uniformly distribution. So you can do what you can construct a uniform distribution if you want to different values of x to different minima and different maxima. For Excel, there is a built-in function as well for uniform distribution. So if I say RAND and then I just keep this parenthesis empty, then I can generate as much numbers as I want between 0 and 1. So you can look at the numbers, and the numbers are between 0 and 1, and that's, and if I can extend it to like that, so you can see that there are a lot of, and whenever I run it again, the numbers will be sampled again. So they are sampled from a uniform distribution where n is in 100 million thousand. So n is a very, very big number. So that's why they are sampled between, there are a lot of numbers which are sampled between 0 and 1. And there is another function called rand between. So between, just like say 10 and 30. So you would always, it would always generate random variables between 10 and 30. So you will always get random variables, but the probability of each random variable would be 1 upon 30 minus 10, selection of each random variable. So there are commands called random and rand between. And if you look at the formula view of rand between, uh, should come under statistical, or I can simply search. If I search rand between, it would give me actually what it actually do. So I need a bottom value, I need a top value, returns a random number between the numbers you specify. Bottom is the smallest integer, rand between will return. So rand between cannot be less than the lower limit, and rand between cannot be higher than the upper limit. So you cannot find any number greater than 30 over here, and you cannot find any number less than 10 over here. So if you want to help on this function, search for help for this function. So this is the rand between function. This is the syntax. This is the formula. So you can always look at the rand between function and the random function. So in order to get sample uniform distributions from different, or in other word, or if you want to, you can always calculate the uniform distribution, discrete uniform distribution by using your own pace on a sheet. the uniform distribution which is discrete. So what you need to do is just to find and how can we find the CDF for this particular example? CDF is quite straightforward to calculate. So just add this value to the previous value, and if you drag it down, you will get the, I don't know, between 10 and 20 there is something funny going on. I think the interval is very low, which is physically not possible. I think that's what I think. I've done something new over here. If you sum all of these values, oh god, I have to take three cells. If you need to sum, no, it's not doing that. Why it's not doing that? So to take sum like that, this is the way cumulative sum is being calculated. Take this value and the previous value. Take this value and the previous value. I've done it over here. Um, so this is like that. E10, E9 plus C10, and then again E12. So the previous value plus C13. So let me write down in so that would be J2 plus I3. Let me change the order of the formula and see what happens. And over here it would be J3 plus I4. No, it's not summing it. Oh God. Anyways,
सर शायद सम लिख कर करें तो शायद हो जाए.
यार सम कैसे करेंगे क्यूमुलेटिव, जरा मुझे बताओ.
इक्वल टू सम और
Hmm.
I3 I2 करके,
Sum I3 I2.
जो आप
Hmm.
फॉर्मूला लगा रहे हैं.
I3 J3. So
और
I'm at
जे J2.
J4. It should be J4 and I3 and I5. Isn't that the case?
यस सर, शायद हो जाए इससे.
हाँ, सम का फॉर्मूला चल रहा है यहाँ पे. थैंक यू वेरी मच. सम का फॉर्मूला
वेलकम
चला.
सर.
हाँ, सम का फॉर्मूला चल रहा है यहाँ पे. So you can find CDF by using a sum formula. Thank you very much from Abdul Rahman, I think. I don't know. Who was that?
सर अब्दुल रहमान.
Abdul Rahman. So you can find by using some formula or some simpler formula. So you can always, what you can do is to find the CDF, and you can always find PDF by using this formula. So similarly for the triangular distribution, I think I gave you an exercise on triangular distribution. Am I right? You have been given in class during recording. I gave you some example for triangular distribution between 50 and 60, if I remember this example. So
यस
the
सर.
the values would be calculated by you. So the formula for PDF was being employed, and you got these values by estimating the formula values from those from those PDF values. Similarly, for exponential distribution, you can have it over here. Tab is that you can always get for a minute. So you want to sample say 10,000 points between 31 and 35, and I want to store it in C1. So I will get some points which are random variables between 31 and 35. What should its graph would look like? Is there anyone who can tell me? If I plot a histogram, how should it look like? कैसा होना चाहिए इसका histogram for a uniform distribution?
Or bell shape.
I am talking about uniform distribution.
लीनियर होना चाहिए ना, लीनियर होना चाहिए ना सर, ऊपर से मतलब
हम्म,
स्क्वायर।
ऐसा होना चाहिए,
सीधा होगा बिल्कुल।
जस्ट लाइक अ रेक्टेंगल।
तो लीनियर मतलब सीधा ही बोल रहा हूँ।
यूनिफॉर्म डिस्ट्रीब्यूशन का मतलब ये होता है कि एवरी वैल्यू हैज एन इक्वल चांस ऑफ गेटिंग सिलेक्टेड. So in a die rolling experiment and in a coin tossing experiment, say example, you look at the die rolling experiment. So random variable would be, in that case, random variable what you can get is 1, 2, 3, 4, 5, 6. What is the probability of getting each? It is 1 divided by 6. What is the CDF of each value? That would be the sum from next line. That would be the sum of, as Abdul Rahman suggested, this and this. And then if I keep it dragging till down, then the cumulative probability will become 1 at the end. And individual probability is 1.166. So if I plot it, what would I get? So this type of plot. So each element has a has equal chance of getting selected. So this is what we call uniform distribution. So you can see that the probabilities in every case is always the same. So this is how could be some to the PDFs and CDF. So if you look at it, what would we expected? We expect this histogram to be something like a rectangle. So this is the case. So why it is not exactly like a rectangle? Is there anyone in the class who could answer? हाँ भाई. Because we have done sampling, and sampling and a representative sample represents the distribution, but it's not guaranteed to be exactly the same distribution. It might have slight differences from the parent distribution, which can be the so this issue can be addressed by increasing the sample size. If you remember, I told you sampling distribution of sampling mean, and I said that if I increase the sample size, or if I repeat the experiment multiple times, you will get a true picture of the underlying distribution, which is actually at the back. So I'm not removing it for, oh sorry, once again, if I again do that, generate random data of uniform, and if I increase two more zeros, that would be quite hard, by the way. It's done. And if I increase it, then you can see that the histogram would be more, now it's more looking like a rectangle. Is it clear? Is it clear to everyone?
Yes
Yes
sir.
sir.
So the bigger the sample size, the better the approximation of the parent distribution. We can check it this thing immediately right now by looking at the data of normal distribution. So I'm talking about normal right now, and I need to calculate PDF. I don't need to calculate CDF. By the way, no, I think it's not generating it. It should be in random data. Yes. So how many rows I need to generate? Say I only generate 100 rows, and I store in C2, and the mean of the normal. What would be the mean of the normal distribution? Is there anyone in the class who could say mean and standard deviation for me? Please suggest a mean.
33 ले लें सर।
Standard deviation.
1.5 ले लें।
1.5 is done. Now, if I plot it, what should it look like? I don't want answers from only two or three people. I want answers from different people. How about if I plot it, what should it look like? It's a normal distribution, so it should look like a bell. Bell जैसी अकल हो गई तुम लोगों की. So this is a normal distribution. Do we have a bell-shaped curve over here? Where is the mean? 33. Where is the standard deviation? 1.5. So I should have 66% value between 31.5 and 34.5. And I should have 95% values between 30 and 36. Mean plus minus 1 standard deviation, 66% values. Mean plus minus 2 standard deviation, 95.5% values. Mean plus minus 3 standard deviation, 99.95% of values. You remember that empirical rule? Does this look like a bell-shaped
Yes,
curve?
sir.
Does this look like a bell-shaped curve?
लग रहा है मतलब इतना नहीं, अगर ज़्यादा वैल्यूज ले लेंगे तो और
It's
लग रहा है।
it's not evident. It's not evident to be a bell-shaped curve. It could be a distorted exponential function. It's not looking like a bell-shaped curve. So what is the problem? So the problem is we don't have much data. This is the only problem. So if I generate rather than 100, if I generate 100,000 by using same mean and same standard deviation, the histogram look much more like a normal distribution. So that actually is very important to have a sufficient sample size in order to predict sufficient and random sample size, unbiased sample with sufficient amount of entries or samples drawn, sufficient number of samples drawn from the distribution in order to look at the shape of the distribution. Its mean should be around 33. Isn't that the case? 32.4 is over here. 33.4 would be something over here. So slightly behind that, it's over here in this bin. This is the mean, and almost 95.5% values should come between what is the standard deviation. So it should be between three standard deviations. So go 4.5, subtract 4.5 from 33. So that would be 28.5. So between 28.5, which would occur somewhere over here, there is 28.5 is over here, the next bin. And 33, 34, 35, 36, 37.5. If you look at 37.5, it would come somewhere over here. Between 28.5 and 37.5, you will find almost 99.5% of the total data. So is this evident from this graph?
Yes, sir.
Thank you very much. So this is how can we, I mean, I'm doing, I'm putting too much stress on distributions, and you will see why after one or two lectures. Similarly, we can do the same for the exponential distribution. We can find the PDF of an exponential distribution if I know the random variable. So let's do that as well. I don't know whether you remember. So someone did for exponential, by the way. Yeah, so I did it for exponential for inter arrival times in a shop between 9 a.m. and 10 a.m. and how many customers we can get if the average customer is 5. If between 9 a.m. and 10 a.m. we can have 5 customers, then how can we find an exponential distribution for customers between 0 and you know that exponential distribution is unbounded from above and it is bounded from below. So it's a count data, and if you look at that, so the probability of getting 22 customers between 9 a.m. and 10 a.m. is quite low. less than 0.2% chance. So for over here, if I over here, so it's almost getting 15 customers between 9 a.m. and 10 a.m. provided that the average number of customers is 5. So the probability of getting 15 customers is just 1% over here, and it would decrease. What would happen if I set m to 10? क्या होगा? कोई मुझे बता सकता है? What would happen to the column C? So when m was 5, the probability of please, I want to learn. I mean, I want to hear from someone. Is there someone who wants to talk about that? So when we were looking at m equals to 5, the probability of getting zero customer was 20%. The probability of getting one customer was 16%. The probability of getting five customer is around 8%, 7.3%, and so on and so forth. When we look at m equals to 15, then the probability would change. So probability should get more values towards that. So if I just plot it till here, you can see that, so I have on average 15 customer could come. Then what would be the probability of having zero customer? So having zero customer is around 0.07, and for 15 customer, the mean of the exponential distribution comes like that in the beginning. Sorry, in around over here. So this is the mean of the normal exponential distribution. If we stop here for a minute and look at the mean, median, and mode of an exponential distribution, then this is actually what I was talking about. So this is what I was talking about. So mean would occur somewhere over here. Median is since 50th percentile, so it will always occur at the 50%, and mode will be a bit more towards the higher values. So mean will always come somewhere over here. So if you plot it, I mean, I haven't included much data, but if I include, um, you know, if I increase the data, then it should look like that. What's actually you see it over here. Then the mean would come somewhere, 15 would come somewhere over here. So this is the mean. Median would come. So median is the 50th percentile of the data. So we can see that where the 50th percentile would occur, and then the in terms of probabilities, and then the median would occur slightly behind. So this is how an exponential distribution curve look like. You should all be very good at looking at distribution. You should all be very looking at the shape of the distribution. You should all be comfortable with the PDF of a distribution. You can try it on Excel. You can try sampling by using Minitab. You can try sampling. You know how to sample. I mean, using computer a lot more than me. So sampling from exponential distribution in Excel. So there is one, two, three videos. Exponential distribution, real statistics using Excel. Just any random website I clicked. So this is exponential distribution. It is the probability density function of the exponential distribution. How can we calculate PDF? How can we calculate CDF? So there are some functions given over here. You can do it on dist. This is the function. You can apply it in MS Excel. These are the properties. Mean is 1 upon lambda. Median mode is like that. Range is between 0 and infinity. So it is bounded above and unbounded below and unbounded above. These are some properties. The cumulative distribution function is like that. 1 minus e to the power minus lambda x. So these are the functions, and you can also Excel provide the following function for the exponential distribution. Okay, let's search for the functions. If I try searching for any function, so expound distribution function is over here. X lambda cumulative. This is exponential distribution. X lambda cumulative. So you can try it by yourselves rather than writing the formula manually. You can sample from exponential distribution from here. You can. I think you would be able to sample from. I don't think triangular, normal. It should be Gaussian like that. No, normal. So normal distribution is over here. Norm disk is the function. Norm inverse. Norm dot disk. X mean standard deviation and cumulative. You know that how many parameters we need to sample from a to completely define uniform distribution. We need only two parameters, maxima minima. How many parameters we need to completely define an exponential distribution? Only one, lambda, which is the mean and the standard deviation. How many parameters we actually need to define a normal distribution? We need two parameters, mean and standard deviation. How many parameters do we need to completely define a triangular distribution? We need three parameters, minima, maxima, and the most likely or the mode. You should learn it by heart. So you can always get normal distribution by mentioning the random variable x, by mentioning the mean, by mentioning the standard deviation, or whether you want cumulative CDF or not. It will only generate PDF if you set it off. So you can generate these distributions quite easily by using Excel. I cannot, come to your houses and then tell you to do that. You have to do it by yourself. This is important. If you don't look at these distributions right now, you will be in deep trouble in the next lectures. This is the only thing I could say. Okay, now going back to the random variates. What are the random variates? Um, there is a problem we usually face when you are doing data analysis and when you are doing simulation that required advanced level data and complex data. So what is the problem? We need to choose some model component behavior of a simulated system, but with a distribution that is right. We don't know from which distribution any data comes. So fundamental theorem of statistics is, if I write any four or five numbers on board, they are coming from a certain distribution. This is standard theorem. Just like the standard theorem of geometry is one of the standard theorems of geometry is every straight line is a very small arc from a giant circle. Similarly, fundamental theorem of calculus denotes the relationship between differentials and integrals. Similarly, there is a fundamental theorem in statistics and random variables and sampling that says that any numbers you have written, any data you have acquired, so you go to uh, some measurement related collect some measurement relation data, and you collect some measurements, different measurement values. So those measurement values which you have just estimated and written down in your PC or in your jotter or notebook, this data is coming from a certain distribution we don't know about. But and this is one thing, you should be sure that it is coming from a distribution. Which distribution is the right distribution? We can't say it this precisely, but we can always guess by looking it into the sample data and by checking some properties of it. So the first and the foremost approach would be to increase the sample size. If you increase the sample size, the underlying distribution, the shape of the underlying distribution, the profile of the underlying distribution would be easier to guess. But there are a lot more things to do. We usually never know for certain what right distribution is, what is right. If we have data from a reference system, usually want to match the data. So for example, you have data from measurements of doors, measurement of roads, then you saw that okay, it's a measurement data, and the roads have certain lengths, fixed lengths, so I can always match it from that. But if you are measuring something which is, or counting something which has no reference system, you can do that quite easily. May want empirical or theoretical distribution. If something is not right, say for example, if you are picking some value, so if you are picking flowers from a very very big garden, so you have a huge garden and you need to pick 5 or 10 flowers, and the garden is full of flowers, then we can say that okay, that distribution could be represented by a uniform one, because you went to a garden and every flower is equally likely to be plucked. So this can be represented by using a normal distribution roughly. If you plug enough flowers, so say for example, if that garden has 100,000 flowers, and you pick some of the flowers you like on your way, on your course to looking at different parts or different areas of the garden, then I can, so for for this type of sampling, I can always use a uniform distribution. For measurement data, we usually go for normal distribution, because measurements can be greater than the the fixed value, the original value, and measurements can be less than the true value, or the fixed value. So you can have chance of getting data which is less than the mean, or you can have chances of getting data which is greater than the mean, and it's equally likely to get both type of estimates. So estimates that are uh, slightly more than the average, and estimates that are slightly less than the average. So for this type of case, it would be best represented by a bell-shaped curve, and that bell-shaped curve would be represented by a normal distribution. So this is the problem. What how can we choose the right distribution? Is there anyone, I mean, now you know why I was stressing so much about the distribution, because we would be talking about advanced features of distribution. Okay, now known characteristics of data help. Is the data discrete or the data continuous? If you have a count data, okay, I have a count data, and it is unbounded from, it seems to be unbounded from the top. So it can be represented by Poisson distribution or exponential distribution. The data is discrete, data is continuous, that would matter. Whether it is bounded, whether it is non-negative. So in order to get a Poisson distribution and exponential distribution, it should always be non-negative. You cannot do that for negative numbers. It should, if, whether the data is finite, the range, or infinite. What are the characteristics of the systems? Arrival are usually exponential. Arrivals, arrival of if you go to the airport and look at the arrival times of flights, so they are usually exponential. Measurement errors are usually measurements, they are all usually normal, and interfailure times cannot be negative. So when you start your stopwatch and you look at how many the flights are coming, how many people are coming to a shop or to a grocery store or to a mall, then a person come at 10 past 9 and another person come at 15 past 9, quarter past 9. So inter arrival time between these two, between zero customer and first customer is 10 minutes, and between customer and second customer is 5 minutes in this particular case. So interfailure times or inter-arrival times, they cannot be negative, because the clock is going into one direction. More formal, we use the standard goodness of fit test to match empirical to theoretical. We won't be doing that, but we won't be doing chi-square based test or goodness of fit test. But rather than, we would just be looking at the distribution shape, and we are more interested in acquiring more data from the sample, for the sample, in order to increase our guesses. Less formal, pick something, then do sensitivity testing to see how much. We would do sensitivity testing, but we would do it when we were doing uh, sampling for Monte Carlo simulation. So we would do it by using sensitivity testing. There are simple heuristics. If nothing is known but the range is bounded, use uniform. So we don't know about the nature of the data, but it seems to be bounded between two values. So the first step or the most basic assumption is to use uniform distribution. If little is known, range is bounded, then the second step would be try triangular distribution. So triangular distribution works really well if the data is not uniform, if the distribution is not uniform, there is a hump or the probability has a mode, one thing, and the data set is not enough. So if you have lesser data points, triangular distribution is a very good candidate to try with. If high variance is bounded on left, if it is bounded on left and unbounded seems unbounded from right, and the variance is high. What do you mean by variance is high? So the numbers are 500, 50, 25, 126. So these numbers have a really high variance. If you calculate mean and standard deviation of these four numbers, you will get a very high standard deviation and very high variance. Then we can try exponential distribution. So these are the characteristics. Thus far, we mostly focused on generating random variables. So far, mostly we use RA and D is equals to RA and D, and we leave the parenthesis open in Excel to generate the uniform distribution random variables. But what about other distributions? There can be several techniques. So what I was attempting in front of you was a part of a learning process. So how can you do it by hand by yourselves? There are built-in functions as well. But that was just a part of a learning process. I always do with the simulation class to try and then try and leave some open questions to you. So if you can try by yourselves and then you stuck on that, then you can always use Google search engine or somewhere else and read some literature to get to the true point. But we can generate for other distributions as well data. Several techniques. One technique is you already know by using Minitab. There is another technique. What you can do is that you can Google just like I did. So there was expon dot distribution and normal dot distribution. These type of built-in functions in Microsoft Excel. Um, Basic idea. What is the basic idea? That we are sampling from potentially infinite population. So the sample size is really big. Am I audible to all? आवाज आ रही है मेरी?
Yes, sir.
Okay. So the question is, how many numbers are between 0 and 1? There are usually infinite numbers assumed. Assume we always working with sample. Some samples are typical, some are not. So typical means some samples are representative. Some samples have only a particular characteristics. Say for example, for that uniform distribution, if I sample for numbers only less than 10, then you could have seen a very different picture. If I sample numbers only from less than 10, and if I sample numbers only between 60 and 80, then that won't be a representative sample. This would be only so between 50 and 60, if I sample this, sorry, 50, 60 and 80, if I sample this and this and this, sorry, this not like that. So the 81. So say for example, I sample only these 5 or 6 values. Would you be able to guess from which distribution it came? Bhai, that would be almost impossible just by looking at the probabilities and the number of samples. So this is important to look at the problem like that. Uh, Toss a coin 100 times and get say 65% head. This is unusual, but it's possible. We can do this often and keep score. We will sometimes get too many heads. कभी ऐसा नहीं हो सकता ना. So if the probability of getting head is 50%, so you cannot get 2.5 heads when you toss it 5 times. So sometimes you get too many heads, sometimes you might get too many tails. So as the number of experiment repetition, which is n, approaches infinity, the relative percentages of total, we would generate an approximation of the PDF. So this is how a PDF is constructed. If you repeat coin tossing experiment 100, 500, 600 times, then and you calculate the probability of getting ahead again and again and again, then you will generate an approximate distribution, and you said, okay, it is converging towards 50%. So that would be the PDF for the distribution. So each distribution has its own characteristic PDF. We have seen it in the previous slides. Each has a total area of 1 because it's a probability distribution. So for all of the sample space, the cumulative, or for all of the elements in the sample space or random variables in the sample space, the cumulative sum of the probabilities of individual random variable would always equal to 1. If we integrate the PDF, we will get, if we sum it, we will get the CDF. This is useful when we want to generate random data with some distributions. Suppose we are simulating activity at a local restaurant. People are arriving in groups of various sizes, want a simulation of that procedure, similar behavior. So I want to simulate that people are coming into some restaurant and in some groups, and I want to look, I want to simulate that what would happen at weekdays, what would happen at weekends, what are the peak hours for, I would find rush at that hour, so I would have more dishes ready. I would have more staff. If I need to appoint a staff, he should work within that peak hours or something like that. So let's assume we have the restaurant arrival data. So we have single customers, the frequency is around 30, and the relative frequency is around 10%. So around 10% chance that out of every one out of every 10 customers is only one. I mean, arrivals per party. So if I have one person coming, so the frequency is 30%. Two people coming, the frequency is 110, or relative frequency is 37%. Cumulative frequency is the sum of 10 and 37, so that would be 47 in this case. Three arrivals per day, people in groups of three. Frequency is 45, relative frequency is 0.15 and 0.62 cumulative frequency, because 0.47 plus 0.15 would become 0.62, and so on and so forth. People arriving in a group of 12, in a group of 8, has frequency of 12 per day and relative frequency of 4%, and cumulative frequency is 4.96 plus 4, that would become 1. So this is a data, a very simple data of arrivals per day. So we are looking at groups of size 1, groups of size 2, groups of size 3 till groups of size 8. और पाकिस्तान होता तो ये वाले ज़्यादा होते. Now, what is the simple code? This is a code in different software, but you can write it in R, you can write it in MATLAB, you can write it in Minitab. So what it is saying, that if x, the value of x is less than, if the value of x is between 0 and 0.1, return 1. If the value of x is between 0.1 and 0.7, return 2, and so on and so forth. So I can do that. Over the long run, this curve will produce the empirical data exactly. Model behavior will not be better than the data, of course. We cannot have a model which works better than the data. The data will always be the best representation. So what is the PDF and CDF in the above case? Say, for example, let's look at this example really quickly. Then there is a condition called if condition. If so, logical test. What is the logical test? I say if D2 uh, or if 0, I don't know how to write less than equal to in Excel. Less than equal to, I think it's something like that. What is X? X. Let's assume X is D2, D1. D1 less than equal to, sorry, less than equal to zero point 0.1, comma, value if true. What I need to return? I need to return 1. Value of true, I need to return 1. Value of false, I don't need to mention it, but anyways, but say 0. Mm. Okay, it will return 0 because D1 is 0. Let's assume R, A, and D And then, so what is the test? If D1 is between 0 and 0.1, return 1, otherwise 0. So it is between 0 and zero point 0.1. How to write less than equal to in Excel? How to write? Now, these are the cons of using a lot of MATLAB and R. I forget Excel. This is greater than, this is greater than equal to. So I was writing right, logical operation right. Value of false. Okay, so this is false because the random value was not between 1 and 0 and 0.1. Let's generate one more. Let's generate one more. So again, greater than that. I hope it is visible. Let me increase the size as well. So the rule was if D1 is between 0 and 0.1, then if it is true, print true. 1 is true. It is 0.9. Why is not coming less than 0.1? Let's corrupt it by yourself manually. Oh God. 0.01 and set it to D2. D2. It's true. Twice. If it is between 0 and 1, then it is true. 2. Good for D1. Let it be 0.5. There is some problem in that. If 0 is between D 0 and D is between 0 and 0.5, is it it's single quotes? I don't know. Okay. Logical value true is it that D F D F. एक्सेल में सिंगल कोट्स लगते हैं डबल कोट्स लगते हैं I think it should be double quotes. Oh God. चलिए अब क्या कह रहा है if 0 is D1 and 0.5 then true otherwise false. It's still false. This is the logical test. Let's see in Excel. I would do it anyways today, whatever it cost. Mm, if Okay, if logical function in Excel okay, if B2 is greater than equal to 60, then pass, otherwise fail. So they use that and they use it in double quotes. So if B2 is greater than equal to 60, then pass, otherwise fail. So I could write some numbers 10, 20, 30, 40, and I write a rule over here. If F1 is greater than equal to 30, comma, then it is pass, otherwise it is fail. And I close it. If I drag it, okay. So if it is greater than equal to 30, then you are pass, otherwise you are fail. So it works well over here. Then it should work well over here. If 0 is greater than equal to D1, greater than equal to, and D1 is less than equal to 0.5, it should be true. If it is 0.9, why it is always saying false?
तो ये 0 और 0.1 डालना है, इसकी जगह आप वो कर देना, मतलब सेल्स के नाम दे देना, जैसे A1, मतलब उसको असाइन करके।
तो मैंने यही तो दिया है, डी में तो रैंडम नंबर जनरेट करा रहा हूँ।
यानी 0 और 0.1 की जगह भी ना आप कोई सेल का नाम लिख दें, जैसे A1 0 डाल के और वो A1 लिख दें। मतलब हर एग्जांपल में ऐसे ही A1 B1 ऐसे लिखा हुआ है, वैल्यू ऐसे लिखी है।
0.1 करके देख लेते हैं। इसको B1 कह दें, उसको कह दें B2. Still is doing the same. You know, if it is B1 and then B2,
B2 बढ़ाए ना भी तो एग्जांपल वो
0.04 में भी
नहीं अभी सही से तो गलत भी बता रहे हैं, मतलब नहीं हो रहा है।
पता नहीं। अब देखो ना, कभी कभी छोटी छोटी चीजें जलील करा देती हैं। अब ये इतनी छोटी सी चीज है। इफ की कंडीशन डबल ऑपरेटर पे लगती कैसी है, इसकी कोई एग्जांपल देख लेता हूँ ना। इफ फंक्शन इन एक्सेल
तो ये ना दो कंडीशन पे नहीं लगती होगी शायद
ओके।
इस तरीके
हाँ,
से।
मेरा ख्याल से दो कंडीशन में लगेगी, ऐसे लगेगी। देखो, मेरा ख्याल से D1 इज ग्रेटर देन D1 एंड के लगेगी
ऐसे शायद ऐसे ही कुछ होगा, नहीं तोड़ तोड़ के नहीं।
0.02। नहीं भाई, तो मैं सही करके दे दूंगा इसको। मैं जरा पढ़ूं, क्योंकि इसने मेरा जरा दिमाग थोड़ा घुमा दिया है। अभी लेक्चर का बहुत टाइम लग जाएगा। सो आई वुड रीड इट एंड आई वुड फिक्स इट एंड आई वुड गिव इट टू यू। नाउ इट्स अप टू मी। So what I would do is that I would construct these conditions for the table. If x is between 0 and 0.1, the arrival should come as 1. If x is between 0.1 and 0.7, the arrival should come as 2. If x is between 0.47 and 0.62, the arrival would come as 3, and so on and so forth. I think जैन तुम सही कह रहे हो, डबल कंडीशन नहीं लगती इस पे। एक कोई ट्रिक होगी इसकी, वो देख लेंगे हम।
बस यही होता है।
डबल कंडीशंस पे ला लेंगे। चलो खैर, बहरहाल I can't argue with that, with the software. whether it's allowing me to do something or not. Okay, now coming back to the PowerPoint. So what I was trying to do is to regenerate that by using MS Excel. I can do it comfortably by using MATLAB. I can do it comfortably by in R, but I think I was struggling in Excel. Let me fix this code and then I will get it back to you. It's up to me. What type of simulation we use in this type of this type of problem, since it is not since this problem is not a measurement data, this has account data, and arrivals can be something. So there is no condition that nine a batch of 9 can't arrive in a party. There is no condition that a batch of 15 can't arrive in a party. There is no condition that a batch of 20 can't arrive in a party. It is highly unlikely, but it is not impossible. You know what I mean? What is the difference between highly likely, unlikely, and impossible? So having minus 4 people coming to the party, it's impossible. Having 0% coming to the party is possible. Having 50 people coming in a cluster of 50 in this party is possible. It would have a very low probability value, but it is possible. So this seems to be unbounded from the right, bounded from the left, and it is the count data. So for that particular case, we will always use Poisson distribution. We will always try to use exponential distribution in these type of cases. So this type of process is called Poisson process. It is widely used in simulations. It assumes that arrival occurs one at a time. So one person, when a cluster of one is coming, now no one else was coming. When cluster of five was coming, at that point in time, no one else was coming. So it samples the arrivals of those clusters in our example with respect to time. The number of arrivals between t and t plus s depends only on s, not on t. So what is t? T is s is inter arrival time. So the next arrival depends upon the inter arrival time. The arrival frequency do not change over time. The number of arrivals in non-overlapping time, the intervals are independent random variables. So if a group or if a cluster of 5 people arrive, then that doesn't mean that the next group would be of 6 people or next group would be of 4 people. There can be any number of people in the next coming group. So they are independent random variables. It's a memory-less property. That's why it is called memory-less function. So lots of arrival in one interval are not made up for the next. It doesn't matter how many cluster of people arrive in a certain time step. It has nothing to do with the next cluster of or next lot of people arriving at the next time step. So this process is said to be Poisson process, and then we can always use Poisson distribution. You should know this really well. We can always use Poisson distribution to estimate the expected arrival times and the duration. Now we would talk a bit more about in this topic when we would be looking at discrete event simulations. Now the next topic is uniform distribution. What is PDF? What is CDF? And what is the mean? This is the mean of uniform distribution, a plus b upon 2. What is the standard deviation? Standard deviation is b minus a upon 12. What are the assumptions for exponential distribution? The probability that an event occur during t and t plus time is alpha into dt. Alpha is constant and independent of t. So this is the inter-arrival average time. The probability that more than one event occurs in this time interval approaches zero as delta t tends to zero. So the smaller the time intervals, the lesser the chances of an arrival. So this is the PDF of exponential distribution alpha e to the power minus alpha x. This is the CDF 1 minus e to the power alpha x. This is the mean. I think we have the mean. No. So this is the next arrival time. We will talk about it in later detail when we will be looking at Monte Carlo simulation and stochastic simulations. So we will look at this slide. We will come back to that slide. This is normal distribution. This is the PDF of normal distribution. Normal distribution has two important variables, mean and standard deviation. So it is all being constructed on mu and sigma. 2 is constant, pi is constant, x is the random variable you are looking at, 2 is constant. So what else remains is mu and sigma.